Welcome. I want to start off by considering an interesting scenario here that's going to help motivate our discussion in this section. So, suppose through accounting procedures, it's known that about 10% of the employees at a store are stealing. Now, the managers would like to fire the employees that are stealing, but their only tool in distinguishing them from the honest employees is a lie detector test that's unfortunately just 80% accurate. Okay, so suppose they run some employees through the test and 13 of them failed the lie detector test, right? Failing the lie detector test is saying that you're not telling the truth. How many of those 13 employees should the managers expect to be thieves? This is a little bit of an open-ended question here, but just to kind of motivate the discussion, let's think about this. There's 13 employees that fail the lie detector test. How many of those 13 should the managers expect to be thieves, right? Naturally, we don't expect all of them to be thieves, per se, especially if the test is known to only be 80% accurate. So here are some things that common ways people will approach this, right? So some common initial thoughts, I guess. I'll say it this way. One of them is that the test is 80% accurate. So, test is 80% accurate, right? 13 of these employees ended up failing a lie detector test. So you would say, well, it worked for 80% of those. Test is 80% accurate. So 13, if it's 80% of those, what's 13 times 0.8 going to be? Grab the calculator here. Not quite prepared with that. 13 times 0.8. 10.4. So 10.4, and you could say that's, rounds down to 10 or rounds up to 11 if you're talking about actual people, right? But 10.4. So there's one common thought. Test is 80% accurate, so there's that. Another common thought that can arise from this is 10% of the employees are stealing, right? 10% are stealing. 10% are stealing. So if 13 of them failed the test, 10% of those people are actually stealing. And so that is 1.3. And then again, you can deal with rounding however you need to there, right? So those are just some common thoughts that are reasonable common thoughts at first glance. However, there's actually a lot more going on here. All right? There's a lot more happening in this scenario, okay? So let's think about how we can break this down. And I'm going to choose to use a tree diagram. I'm going to choose to use a tree diagram here, okay? I'm going to choose to use a tree diagram. 10% of the employees of a store are stealing. So let's see here. You can either be a thief or an honest employee. You're either a thief or an honest employee, right? If 10% of the employees are store stealing, then we can draw weighted probabilities on these branches of how likely it is that we'll move on down here. So far, so good, I think. 10% of the store employees are stealing, right? So you're either a thief or honest with these probabilities. All right? Now, the lie detector test is 80% accurate. The assumption here is that no one's going to offer up themselves in the lie detector test. It is 80% accurate, right? So for these thieves, right, you can either pass the lie detector test or you can fail. And we're assuming everyone is saying, I am not a thief, right? So how many of these thieves will pass the lie detector test? Well, if it's 80% accurate, 20% of them will pass it. 80% of them will fail it. Similarly, these are the same results for honest employees, unfortunately, right? Is that if you're an honest employee, how many of them will pass the lie detector test? Think about what it means to pass the lie detector test as an honest employee. Most of them are honest, right? And they're telling the truth. 80% of them will pass. If you are an honest employee and you are saying I did not do it, 20% of the times it will be not correct and you will be failing. Notice the flip-flop on these percentages here, right? Because if you're a thief, it should be correct 80% of the time, right? The lie detector test is accurate 80% of the time. So if you're a thief, It should be correct 80% of the time, and being correct if you're a thief is failing, right? Being correct if you're honest is passing the test. So notice the flip-flop on those branches there. That is, in fact, correct, all right? 13 employees failed the lie detector test. How many of those 13 employees should the managers expect to be thieves? Well, let's think about this. 13 employees failed the lie detector test. Well, how likely is it that someone actually just fails the lie detector test? What's the probability of failing the test? Well, you can follow these branches, right? You have basically two scenarios to consider. You're a thief and you fail, or you're honest and you fail. If you're a thief, there's a 10% chance of being a thief, right? And then 80% chance that you fail. Plus, there's a 90% chance that you're honest and a 20% chance that you would fail there. And so we can add those together. This is what, 0.08 plus 0.18, and so that is 0.26. So that's the probability of failing. So there's a 26% chance of failing. Okay. But that's not what we're asking. We have 13 employees who have failed the test. How many of those should the manager expect to be thieves? Well, let's think about this. We are really considering not just the probability that someone is a thief, but the probability that someone is a thief and failed the test. Probability of failing and being a thief. The probability of failing and being a thief. Well, that's exactly just this branch right here. You're a thief and you fail. So that's 0.10 plus 0.80. Sorry, not plus. That should be times. 0.10 times 0.80. 0.10 times 0.80. So there is an 8% chance that they have failed and they are a thief. There's an 8% chance that they failed and they are a thief. Okay, so let's think about this. You have 13 employees that failed the test. You have 13 employees that failed the test. There are 13 of them. How many of those should they expect to be thieves? All right. 13 employees failed the test. How many of those should they expect to be thieves? So this is out of the people who failed, how many should we expect to be thieves? Right? Out of the people who failed. This is not out of everybody. This is out of the people who failed. How many are thieves? How many are thieves? Out of the people who failed, how many are thieves? All right. Well, there's an 8% chance that you failed and you're a thief. There's an 8% chance that you failed and a thief, right? If you're out of the people who failed, you have to be failed and a thief. But it's not 8%. It's going to be 8%. This is out of the people who failed. There's a 26% chance that someone failed the test. And so the desired probability then is actually 8 out of 26. 8 out of 26, which is what? About 0.3077. 0.3077. So in reality, we should expect 13 times 0.3077, or 4 of them, or 4 people. We expect 4 people to be thieves out of the 13, which is maybe a lot less than one would initially imagine, right? Maybe a lot less than one would initially imagine. What is going on here with this little extra division step oftentimes is confusing at first, because this question is out of the people who failed, how many are thieves? You have 13 employees that failed the test. How many of those should the managers expect to be thieves? Think about this in terms of Venn diagrams, right? You have thieves and then fail the test. Failed the test. And then there's this intersection area, right? There's this intersection, okay? So there's an intersection here. Think about where these probabilities go. The probability that someone fails and a thief is 8%. So we know that there's 8% in here. There's a 0.08% chance that someone randomly chosen falls into that category, okay? Now, we are given a set of 13 employees. We're given a set of 13 employees that failed the test. Right? And how likely is it that someone failed the test? We calculated that is 26% chance. 26% chance. So the question that we're really trying to answer is, given that we're inside this circle, given that we're only in this realm, we are only in this realm, how likely is it that we're in this realm? So we're going to take this area divided by the whole area. That area, the intersection area divided by the whole area. This is really just to motivate the idea that there is a reason and a thing of something what's called a conditional probability. This is a conditional probability question. It's not just how many employees are thieves. It's given that you have a set of people who have failed, you already know something about your area, right? You're no longer looking at everything in here. You're looking at just the highlighted circle. Given you know that information, how likely is it that some other event happened? Let's go ahead and write out this definition here. The probability of an event B occurring when it is known that some event A has occurred, that some event A has occurred, is called conditional probability. Conditional probability. Conditional probability. And this is denoted the probability of B given A. Given A. And this is actually definition 210. If you want to correspond to something in the text there. This is definition 210. Definition 210. Definition 210. Probability of event B occurring when it is known that some event A has occurred is called conditional probability. It's denoted probability of B given the event A has occurred, and it is the probability of the intersection divided by the probability of the given event, provided that the probability of the given event is non-zero, provided the probability of A is greater than 0. All right. There's our definition, conditional probability. It is the probability of the intersection divided by the probability of a given. I always like to try to relate this to Venn diagrams, to think from a Venn diagram perspective. It sort of makes sense that we're dividing out, how likely is it that we're going to get this 0.08 when there's a 26% chance that we are in this giant circle, and there's an 8% chance we're in here. So what is that ratio? 0.08 divided by 0.26. Let's take a look at some more maybe entry-level examples then, to try to help dissect and understand conditional probability. Let's see here. Let's say we have a two-way table of information about some people. Some are employed, some are unemployed. We've got male category and a female category for now. We'll just go with that real quick. And there's some, so what do we know here? There's 460 here, and there's 40 there, 140, and then 260. Okay. And let's say that M is the event that, if you select a person at random, let's say M is the event that a male is chosen at random. And let's say E is the event an employed person is chosen. Let's say E is the event that an employed person. Let's try person again here. Let's make this legible if we can. Employed person. I know my handwriting is not my strong suit, but usually it gets better as I'm recording more and more lecture videos as the semester goes on, but it has not yet. Male is chosen. Event M, event E, that an employed person is chosen. Okay. So let's go ahead and find probability of E happening, and then let's find the probability that M given E happens. All right. Let's start out with the probability that an employed person is chosen. Let's take a look here. Well, how many employed people are there? Well, there's 460 males and 140 females on here, so we could do a quick subtotal here. That's 600 total there. How many are unemployed? 40 plus 260 is 300. So there are 600 employed, and there are 600 plus 300 total people, or 900. So we're looking at 600 out of 900. 600 out of 900, or there's a 2/3 chance that we select someone at random, we'll get an employed person. All right. What's the probability that it is a male given it is employed? Probability, then, of a male person being selected given you've selected an employed person. Well, according to the conditional definition above, this is the intersection of the two events divided by the probability of the given. The probability of the given is prob P of E. P of E. All right, so we know that P of E is 2/3. Just computed that. What's the probability of the intersection? So probability that an employee is male and employed. Well, there are 460 male that are employed out of a total 900 people. Out of a total 900 people. So what is 460 out of 900 here? Running that through a calculator. 23 over 45. Divided by 2/3. Dividing by a fraction here is the same thing as multiplying by the reciprocal. So 23 over 45 times 3/2. And that is 23/30. 23/30. All right. There we go. Nice. Let's try one more. One more kind of quick entry-level example here. Let's say that the probability that a scheduled flight departs on time, a scheduled flight departs on time, is probability that it departs, we'll say capital D for departing on time, is 83%, or 0.83. The probability that it arrives on time, is, say P of A, probability of arrival for capital A for arrival, is 0.82. And the probability that it departs on time and arrives on time, that's D intersect A, is 78%. So let's find probability of A given D, and let's find the probability of D given A, and compare. All right. Probability of A given D, conditional probability, is the probability of the intersection divided by the probability of the given event. Keeping track of that. So this time we're given that it departed on time. So the intersection probability is 0.78 over the probability of D, which is 0.83. So I got the 0.78 and the 0.83 there. And run that through a calculator. That is 94%. 94%, okay? Does the order matter here? Is the probability that it departs on time, given that it arrives on time, different? Well, I would say yeah. Right? The intersection is the same. D intersect A and A intersect D, that's the same region. But we're dividing now by a different probability. We're dividing by the probability that it arrived on time. So this denominator is going to change to 0.82. The probability that it arrived on time is 0.82. 0.82. And so then this is equal to 95% if you run that through a calculator. Okay. The order matters. Be careful on your conditional probability statements when you're writing these things out. If it's A given D or D given A, that matters because it's going to decide what event you're dividing by in the denominator, or what probability rather, okay? We're going to leave it at that for now, just kind of an introductory video on conditional probability. There's going to be a couple more videos to come here on this section. So let's pause there for now, take a quick bathroom break, and come back in a couple minutes, and we'll see you in the next video.